So today we're going to learn about perpendicular bisectors. We previously learned about a midsegment, which was a segment inside of a triangle. And now we're going to learn about a perpendicular bisector, which can and cannot, doesn't have to be inside of a triangle. The first situation we're going to look at it in is not within a triangle. We're just going to define it. So let's define it, and then we will look at the picture and draw it. So first, a segment bisector is a segment, ray, line, or plane that is perpendicular to a segment at its midpoint. So this is a segment, ray, or line that is perpendicular to a segment at its midpoint, and it is called the perpendicular bisector. So again, the name perpendicular bisector tells you exactly what the segment is doing. All right, it's going to be perpendicular to a different line or segment, and exactly right where it's perpendicular to the segment, it's also going to be cutting it in half. So if we look at this picture over here, and let's just say we have segment AB, and we have this line SP here. We know that if we have a segment SP and that it is perpendicular to a segment, so there's perpendicular, and it's perpendicular at its midpoint. So the only way we know that that is the midpoint is indeed if the lines there are marked congruent. So right now, this segment SP, all right, is the perpendicular bisector of segment AB. So basically the way you want to look at this is that SP is the knife and it's cutting AB in half. So whichever one it tells you that SP is the bisector, then that means the other one is the one getting cut in half. We don't know anything about SP, we just know AB is cut in half. Now a way to use this segment is, all right, so if a point is on the perpendicular bisector of a segment, then it is equidistant. And again, all equidistant means is equal distance. It's just kind of two words, you know, made up. So instead of saying equal distance, we just say equidistant. All right, and it is equidistant from the endpoints of the segment. So again, let's read that. So if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints. All right, so we have a segment. We have a point that is going to be on the perpendicular bisector. Now the point doesn't have to necessarily, the line doesn't have to necessarily go through the point. You just have to know that the line will for sure indeed extend through the point because of the properties that it has. So basically, if this is a perpendicular bisector, so let's make that our perpendicular bisector, then we know that from A to D is going to be equidistant from B to D. So this length AD is congruent to DA. So if, and let's give this two letters, so if segment DE is the perpendicular bisector of AB, then segment AD is congruent to BD. So again, what this says is that if you have a point right here that is on the perpendicular bisector, and again, we only know it's the perpendicular bisector because of the markings here, perpendicular bisect, then this point is equidistant from the endpoints of the segment. The converse of that is the perpendicular bisector theorem. Converse, remember again when we say this converse, we're basically taking this first statement here and we're just switching the order of it. Converse, again, is just kind of think of the suffix there as converse and reverse. So basically, if you know that a point is equidistant from the endpoints of a segment, So basically what that's saying is that we have this point, and we already know, now we're going to start with this. We know that the point is equidistant to the endpoints of the segment. Then we can conclude that that D lies on the perpendicular bisector. So if you know that DE is indeed the perpendicular bisector, then you know it's equidistant to the endpoints, and vice versa. If you know it's equidistant to the endpoints, then it is okay for you to conclude that DE is indeed the perpendicular bisector. So if you know that DA is congruent to DB, then we know that DE is the perpendicular bisector of segment AB. So that's basically the definition and some theorems behind it. So now, of course, we're going to look at the numbers. So in this first example, we're going to use the perpendicular bisector theorem. It tells us here that BD is the perpendicular bisector of AC. So right away, as soon as you see this, you're going to take it over here and you are going to mark your picture. So mark it. If it tells you it's the perpendicular bisector, I want to see proof of that over here on the diagram. So you mark that as, okay, it's perpendicular and it's bisecting. So that would be marking the perpendicular bisector. You put the box at the 90, and then you put the little tick marks on the segment. So that's the perpendicular bisector of AC. They want us to find the length of AD. So we're having to find the length here of this side. Well, we know that BD is the perpendicular bisector. We also just talked about that perpendicular bisectors, that this point is equidistant from the ends. So basically this side here, AD, is congruent to CD. All right, so we have AD is congruent to CD. So remember, anytime you have congruent pieces, they have equal measures. So you're just going to put 3x plus 14 equals 5x, and you're going to solve. Remember, if it's by itself, you don't move it. So we're going to subtract 3x, subtract 3x. So we have 14 is equal to 2x. Our x is 7. The question again said find the length of AD, so we have to use that 7 and plug it back in over here for AD. 5 times 7, 35. That's using the perpendicular bisector theorem. You set the sides, and what it looks like it's a triangle. So here, you know, these sides, they're equal to one another. Example 2. So in the diagram, WX is the perpendicular bisector of YZ. So again, they're giving us a lot of information there. So we're always going to take that information and we're always going to mark the picture. So it is, so there you go. It tells us right there already perpendicular, and we're going to mark bisector. So basically what this diagram is trying to get you to visualize is that if XW is the perpendicular bisector, then this line is going to keep extending in the exact direction that it's going because of that 90-degree angle. And when that happens, this line then keeps continuing right through that point. So now they're asking, what segment lengths in the diagram are equal? Well, if it's a perpendicular bisector, here we've marked those. Now we also know that it is equidistant to the ends. Well, we also have another point on the bisector. So these pieces are going to also be congruent. So we have here that YW is congruent to ZW. We have YV congruent to ZV. YX is congruent to ZX. So those are all of our congruent pieces. The next ask is V on line WX. So here's our line WX. Is V on it? Yes, it is. Yes, because XW is the perpendicular bisector. Okay, so go ahead and pause the video and see if you can answer the guided practice for examples 1 and 2 down below, 1, 2, and 3, and then come back and check. Okay, so let's check. In the diagram, JK is the perpendicular bisector of NL. So again, here we go, perpendicular bisector. Want to make sure I take this information, because yes, even though it is 2 words, it's still info. You have to know what is the meaning behind these words. So again, always mark what it means. All right, they're telling us that JK is the perpendicular bisector. So, what segment lengths are equal? Explain your reasoning. Well, if it's a perpendicular bisector, then the point on the bisector is equidistant to the ends. And we already marked these congruent because of the perpendicular bisector. And we can see that these side lengths of 8 are congruent because they're marked with 8. So our congruent pieces here are MN is congruent to LM. Let's see, NK congruent to LK, and NJ is congruent to LJ. And those are all congruent, again, because MK is the perpendicular bisector. All right, in number 2, it asks you to find the length of NK. So remember this question. You need to be able to, when you read this question, read it back as find the length of NK. So to find the length of NK, that's this piece over here. Well, we know that this segment is congruent to this one. We just stated that here, that NK is congruent to LK. So we all know that congruent pieces have equal measures. So we're going to set up 6x minus 5 is equal to 4x plus 1 and solve like the mad solving geniuses we are. So 2x is equal to 6, x is 3. So remember, that's not the length it asked for. It wanted NK. So you've got to take that 3 and we're going to plug it back in. So 6 times 3, 18, minus 5, NK is 13 units. Now explain why M is on JK. So I kind of briefly described it over here, but basically M is going to be on that line because that line is crossing right through here at 90 degrees. So it's going to keep going in the exact same direction it is. It's not going to tilt up any or tilt down any. It's going to go straight through it. So, and it is because MK will extend, okay, from a 90-degree angle. All right, good job.